This is Paul Bamberg welcoming you to the first Math 23 narrated R script. I've already opened up RStudio and opened the first script file on finite fields. I position the cursor on the top line, and to execute a line of the script I hit Control R, or alternatively click the Run button. Lines that begin with a number sign are comments and don't do anything. They're there in order to give you a clearer insight into what the script is doing. We'll begin by considering the axioms for a field and illustrating them by doing a little bit of arithmetic in R. In a field there have to be two operations called addition and multiplication, and they have to obey the usual rules of arithmetic and algebra, which collectively are known as the axioms for a field. Any set of mathematical objects that satisfy these axioms qualify as a field, and later in this script you'll see a field that has only 5 elements, probably different from anything you've seen before. I'm going to set up the plots pane in the upper right-hand corner to display some lines of mathematical text. Don't worry about the details of what I'm doing here. First axiom: addition is commutative. The order doesn't matter, and I can illustrate that in R by adding 3 to 1.2 in 2 different orders. If you look at the lower left pane, you'll see that the answer in each case turned out to be 4.2. Second axiom: addition is associative. That is, when I do arithmetic, either addition or multiplication, I don't have to use parentheses. When I'm adding, I can put the parentheses around 2 plus 3, or around 3 plus 4.2, or leave them out. I get the same answer in any case. Third axiom: there's an additive identity whose name is 0. When I add 0 to an arbitrary element A of the field, I get back A. For example, if I add 0 to 3.14, I get back 3.14. Fourth axiom: every element has an additive inverse. If the element is called x, its inverse is called minus x. Now I'm going to do this in R by using a variable. I am assigning the value 3 to the variable x with that 2-character left arrow. You can use an equal sign most of the time to accomplish the same effect, but not always. So my advice to you is always use the assignment operator, the less than sign followed by the minus sign. Now that I've got a value assigned to x, I can assign the value minus x to y, and when I print out the value of y, I get minus 3. When I add x to y, I get 0. You've probably already noticed that if I write an expression in R and execute that expression, I get the value of the expression down in the bottom pane. Similar axioms hold for multiplication. It's commutative. I can multiply 3 and 1.2 in either order. It's associative. It doesn't make any difference where I put the parentheses when I multiply together 3 numbers. There's a multiplicative identity whose standard name is 1. When I multiply an arbitrary element A by 1, I get back A. And finally, with the exception of 0, every element has a multiplicative inverse. The multiplicative inverse of x is called 1 over x. And if I assign the value 3 to x and assign its multiplicative inverse to y, y has the value 0.33333333. When I multiply that by y, remarkably, I get back 1. I don't understand why I didn't get 0.9999999, but I'm always happy when computer arithmetic obeys the axioms for a field. The integers don't form a field. Where they fail is with the multiplicative inverse axiom. For example, the integer 2 has no inverse that is also an integer. Yes, it has an inverse, which is 1/2, but that's a rational number. It's not an integer. Last axiom: Multiplication is distributive with respect to addition. That is, a times b plus c equals ab plus ac. And I can check this by assigning values to 3 variables in R and multiplying it out. By the way, doing these illustrations in R in no way proves that the axioms are satisfied, because the axioms say this always happens, and all I'm doing is showing you one specific case. If I want to check the distributive law in a slightly different way, I put a double equal sign between a times b plus c and a times b plus a plus c. That double equal sign tests for equality. If the two things on either side of the double equal sign are equal, the value is true, which you can see displayed at the bottom left of the screen. Now let's look at a field that you may not have seen before, a finite field with only 5 elements. And the way we're going to do this is by carrying out what you may have heard of as modular arithmetic. At each step, you divide by 5 and keep the remainder. So working with integers, you always get the answer 0, 1, 2, 3, or 4. Taking the remainder in R is accomplished by a double percent sign. So when I say 2 plus 4, double percent 5, what I mean is add 2 and 4 to get 6, divide by 5, and keep just the remainder, which is 1. And you see at the lower left, I do get the answer 1. Now we can write our own function to do this in R. The secret is to use a function name that begins and ends with a percent sign. Then we can use it as a new operator. So the function I'm going to define has the strange name percent plus 5%. This is addition modulo 5, and I assign to that a function of x and y, for which the rule is add x and y and take the result modulo 5. Now that I've defined that function, I can use it as a function. That is, when I apply the function named quote percent plus 5% quote to the values 2 and 4, the answer I get is 1. But what we really want to do is use this function as a binary operator. I can put it in between 2 and 4 without the quotation marks, and I get back the answer 1. Now let's make a table of addition facts, elementary school style. R has a function named outer that does this automatically. It takes 2 vectors, and the reason we're using R in this course is that in R everything is a vector. So let's look at our vector. V, I use the equal sign here in violation of my own advice, but it works. When I display V, it's the vector whose 5 components are 1, 2, 3, 4, and 5. Now in the finite field with 5 elements, Z5, 5 is an alternate name for 0. Anything that's a multiple of 5 is an alternate name for 0, because when you divide it by 5, you get 0. So I can now call the outer function with the vector v as the first argument, the vector v as the second argument, and our addition operator as the operation we want carried out. And you see we get a nice table at the bottom showing all the possibilities when you apply the addition modulo 5 operator to 2 of the elements in the vector v. This is a table of addition facts where the 5 row and 5 column correspond to 0. You can check that when you add 5 to anything, you get back what you started with. It's the additive identity. You can also look at each row to see that every element has an additive inverse. For example, if you look at row 2, you see that in column 3 you get 0. That's because 3 is the additive inverse of 2 in this finite field. Similarly, we can define a multiplication function, multiply, divide by 5, and keep the remainder. And we can generate a table of multiplication facts. You can see that when you multiply anything by 5, which is an alias for 0, you get back 0. And You can also inspect each row, noticing, for example, in row 2, that when you multiply by 3, you get back the multiplicative inverse, the multiplicative identity 1. So now we have a field where we can view the elements of the field as integers, but every element has a multiplicative inverse, which can also be represented as an integer. It's not that easy to figure out multiplicative inverses in a finite field. Here's a simple rule for doing so that will also illustrate an interesting property of R. If I ask R to add two vectors, it does so component by component. So when I ask it to add v to v modulo 5, v is in the top line at the lower left-hand corner of the screen, and each element in the lower line there is twice the element in the top line. What? Twice 3 is 1? Sure it is. 2 times 3 is 6, which leaves a remainder of 1 when you divide it by 5. Similarly, 2 times 4 is 3. Same thing happens if I ask R to multiply two vectors. V is the vector 1, 2, 3, 4, 5. V multiplied modulo 5 by V has 5 components. 1, 2 times 2, which is obviously 4. 3 times 3, which is 4 because 9 divided by 5 leaves a remainder of 4. 4 times 4, which is 1. Think 16 divided by 5, keep the remainder. Multiply by V yet again. I've got the cube of every element, and what do you know? The cube of every element turns out to be its multiplicative inverse. The cube of 2 is 3, and 3 times 2 is 1. The cube of 3, the third element, is 2. 27 and 2 are the same in this field because both leave a remainder of 2 when divided by 5. And if I raise each element to the fourth power, I get back 1 in every case. This is in fact a mathematical result that goes by the name of Fermat's little theorem. We're not going to prove it at this point in the course, but you might want to try inventing a proof on your own. And that concludes this first script.